Now we have it. Thank you. Okay. So the reason why we are interested in quantum is because quantum can potentially change entire industry. It can disrupt healthcare industry because if we can enable certain drug discoveries through quantum computation, we can shorten the cycle for therapy development. It can disrupt our energy and climate industries because certain catalysts will enable faster carbon capture or nitrogen fixation, solve nitrogen fixation problem. So in order for us to be able to take advantage of it, here at Microsoft, we are thinking about a unified approach which combines AI, quantum, and high-performance computing. So AI for design and optimization, quantum to enable faster computation and enable to generate high-quality data that will be used by AI, and HPC all up basically supports these hybrid workflows and makes the whole approach useful. So we are uniquely positioned to take advantage of quantum by leveraging over 3 components that we are developing within Microsoft. So from the very beginning of this program, we were thinking about full stack quantum machine. It's not about individual qubits or the count of them, but it's about all layers in the stack. They involve building physical hardware, quantum processing units, thinking about quantum error correction and classical compute that is needed for that, and ultimately thinking about the highest layer, which involves applications and making the machine useful for consumer. So at the end of the day, one should think about the CPU, GPU, and QPU all working seamlessly together within our cloud offerings and enable solving commercially valuable problems for us. So of course, for us to be able to do that, we need to think strategically and need to think about qubits bottom up. And so from doing a lot of studies, we realized that we need to build qubits that are small, roughly micron size, that are fast, that are doing operations at the microsecond scale, and most importantly, that are reliable. And that's where topological approach shines, because the idea of topological approach is that if you encode information in these Majorana modes, these exotic quantum degrees of freedom, this information will be inherently protected from or immune from errors and decoherence, which is a difficult problem for all the other platforms. And so in order for us to be able to solve this problem, we had to invent new material stack, new phase of matter that supports these degrees of freedom. And so we're happy to announce that we developed a much better material stack that gives us enormous improvement in qubit lifetime. And we also built a new quantum processing unit with this material stack. And this processing unit is shown here in the picture. And I wanted to showcase it to you right here. This is Majorana 2. So you can see here to the left a quantum chip that is powered by the topological core. Our qubits are digitally controlled. So we couple them with the cryo-CMOS on the same chip, which helps us to solve input-output problems. And the idea is that these qubits, they operate at very low temperature, millikelvin temperatures, and therefore we want to make sure we solve this input-output problem by placing the cryo-CMOS, which controls the operations at the same sort of millikelvin stage as our topological qubits. All right. what is the science behind our qubit? So as I said, we want qubits to be fast, small, and reliable. It's very difficult to satisfy all these constraints. And so, as I said, we needed to invent a new phase of matter, which is called topological superconductor, or in short, topoconductor. So commonly we know phases of matter such as solid, such as liquid, such as gas. But our phase of matter is totally different. It appears when you combine materials such as superconductor, just conventional superconductor, and conventional semiconductor. Superconductor conducts electricity with zero resistance. Semiconductor has electrons, and you can control density of these electrons. But when you combine them together in the right proportions and use magnetic field, we generate a very unique state that supports these Majorana modes, exotic modes, that we encode information in. And so we had to engineer the right, interface between superconductor and semiconductor and make sure that this layered material appears as one sort of phase of matter, as unified phase of matter. For us to be able to support the stringent requirements, we had to develop new recipes for fabrication. Quantum devices, they live or die depending on the quality and depending on the constraints, whether we can satisfy these constraints or not. And so here we are showing device quality that we've achieved last year. And here we're showing where we started from. And you can see that the interface between semiconductor, which is down below, and superconductor has improved tremendously. And that was one of the key ingredients that we had to solve. And we've done this by essentially fabricating our devices atom by atom, as was shown in this movie. So that was the key recipe for success. And this year, we are showing even more improvements by introducing this new material stack. This new material stack has lead superconductor instead of aluminum one. And the key advantage of lead superconductor is that it has parent gap 4 times larger than aluminum. And this difference in parent gap directly translates in a 1000x improvement in qubit performance, as reported in this paper over here. So, we had to introduce new superconductor, but it's not just drop and replace the superconductor. We actually had to change entire semiconductor stack. We switched the substrate. We optimized quantum well. We've optimized all the interfaces in this stack and make it work with this lead superconductor. And all these improvements happened within 1 year. And I have to say, I've been with the program 15 years, and the level of improvement, which was enabled by AI and simulations that happened over the last year, is equivalent to the level of progress that we've made in the first decade of my tenure within Microsoft. So the point is, we are accelerating, we're introducing this changing faster, we are shortening development cycle. And if you are interested in more details, we posted the paper on Microsoft website. This paper also appears on arXiv, and I will encourage you to take a look. So once we have the recipe for the material stack, we want to press on, we want to build qubits out of it. So this is how our qubit array looks like. Our qubits are based on 8 structures that are shown here. So these are superconducting layers that are patterned on top of semiconductor. So here you see a 2x2 array. This 2x2 array is connected by different gate layers, and they correspond to tuning, control, and readout layer. And when we want to do single qubit or 2 qubit measurements, we just activate the right quantum dots, the right layers, in order to be able to do these operations. Also, please pay attention to the scale. Here, the scale is microns. And I already show you that, 4 qubits, they are occupying very small area, tens of microns squared. So if you want to build million-qubit chip, we can put it on a chip on the size of the credit card. So our idea is that the qubits that are of this size and densely packed are able to build one modular structure that is capable of solving, very large, complicated, commercially viable problems. So, so this is how fabricated device looks like. So you see these false color H structures, and you see different gates. As I mentioned, they're used for tuning, control, and readout. And also, you see here data for the lower qubit. We've tuned up the lower qubit, and we've done one of the fundamental measurements on this qubit by connecting this loop that is shown here on the top and measuring the state of the qubit in a Z configuration, in Z basis. And so what you see here is a capacitance trace as a function of time. This is the capacitance that is measured by the readout scheme that we have, RF readout scheme that is very fast. And so we see these small changes in capacitance, and these small changes in capacitance, they correspond to different states of the qubit, 0 and 1. And the important point that I want to make here that the lifetime of a qubit has increased up to a minute, which is enormous on a scale of qubits. So in the previous device based on aluminum, the maximum lifetime that we were able to achieve was 10 milliseconds. Here, we increased this lifetime by a factor, 1,000x more. And this is the power of thinking about everything altogether, from materials to design, enabled by AI and simulations, and optimizing the entire, qubit array. So, so this gives us confidence in the approach. It tells you about the velocity of changes that we are introducing in our program, that you are able to iterate and introduce new material stack, new design, new system, measure the devices just within 1 year. That basically gave us confidence that we can accelerate our roadmap to building a commercially viable quantum machine from 2033 to 2029. So, I will I would like to mention, another thing, that this design was really accelerated by AI. We worked with our partners on the discovery team to use all the design rules, all the requirements, and we optimized over more than hundreds of parameters. And by using some of the tools, AI-enabled tools that were provided by our partners, we were able to accelerate the design cycle for such a system tremendously. And we're able to, design essentially such a complicated chip in less than a month. So, so that's sort of the punchline for the story. Again, as I said at the beginning, we turned the hard physics problem into a roadmap for a scalable quantum computer. And we introduced new materials because we think that the secret to be able to make new devices that satisfy the stringent requirements that are needed for quantum computing at scale is through better materials, through better interfaces, through better fabrication, ground up, through better algorithms, through better designs. And so we are trying to push on all the cylinders and accelerate moving forward. So with this, I want to close the talk and thank you for attention and take questions.